We use the internet literally every single day, right? But have you ever stopped and wondered what is actually happening behind the screen? Well, today, we're going on that journey. We're going to uncover the hidden mechanics, the secret conversations, and all the invisible systems that power just a single click. Okay, let's get into it. So, picture this. You type in a web address, you hit enter, and poof, the website appears. It feels instant, almost like magic. But in that tiny fraction of a second, an absolutely incredible coordinated dance of technology takes place all across the globe. We're going to break that dance down step by amazing step.
So, the very first step, it's probably not what you're thinking. Your computer doesn't just magically go to the website. First, it has to find its address. And to do that, it needs to consult the internet's giant global address book, the domain name system, or DNS for short. Just think of DNS like the contacts app on your phone. You don't remember everyone's phone number, do you? Of course not. You just know their name. Well, DNS does that exact same thing, but for the entire internet. It takes a name that we can easily remember, like example.com, and translates it into the numerical IP address that computers actually use to find each other. And this right here really shows you the split between how we think and how machines talk. On the left, you've got what makes sense to us. On the right, you've got the language of the machines. Routers, servers, they need that super precise IP address to get traffic to the right place. I mean, without DNS, we'd all have to carry around notebooks full of numbers just to browse the web. It's the essential translator that makes the internet we know and love possible.
So how does it find that number? Well, it's kind of like a fascinating little chase. Your computer first asks its local DNS server. That's probably one run by your internet provider. If that server doesn't know the answer, it starts a journey up the hierarchy. It asks a root server, which doesn't know the exact address, but it knows who's in charge of all the .com addresses. That's the TLD server. The TLD server then points to the final authoritative server for that specific website, which at last provides the correct IP address. This whole distributed system is just brilliant because it's so resilient. There's no single point of failure that can take it all down.
All right, we have the address, but our journey's not over. It's really just getting started. Now that your browser knows where to go, it needs to actually ask for the web page. And this is where we get into the language of the web, the protocol that builds everything you see online, HTTP. The easiest way to think about HTTP is to imagine a very polite, very specific set of rules for a conversation. It's a conversation between your browser, the client, and the web server, kind of like a customer and a waiter. Your browser places an order by sending an HTTP request, and the server fulfills that order by sending back an HTTP response, which contains the web page's data. This back and forth, this request-response cycle, it's the absolute core of how the web works. Your browser sends a request, literally saying, "Get me the main page." The server replies with a status code, like 200 OK, which is basically computer speak for, "You got it, here you go." And then it sends all the actual files, the HTML, the images, everything. Every single piece of a web page is fetched this way. Now, here's a crucial little detail about HTTP. It has no memory. It's stateless. Once the server sends you a file, it completely forgets who you are. This was a huge problem for things like, a shopping cart. So what was the solution? Cookies! Those little bits of data are how a website keeps track of you from one page to the next. They're what give the stateless web a memory. The reason the web feels so fast today is because HTTP has evolved so much. The very first version was painfully slow. It needed a whole new connection for every single image. HTTP/1.1 made things better with what are called persistent connections. But the real game changer was HTTP/2, which broke data into smaller frames so a single slow-loading image wouldn't block the rest of the page. And now we've got HTTP/3, making things even faster by using a totally new protocol called QUIC. Okay, so you're on the web page. You've used DNS to find it and HTTP to load it. But now you see a Contact Us link, and you click it to send an email. All of a sudden, a completely different system just springs into action. We're not having an HTTP conversation anymore. We are now using the internet's digital postal service. Meet SMTP, the Simple Mail Transfer Protocol. Its job is very specific, very focused, to send or push your email from your mail server across the internet to the recipient's mail server. It doesn't handle you reading your mail. You can think of it purely as the delivery truck of the internet. So when you hit send, your email program hands that message to your outgoing mail server. That server then acts as an SMTP client. It finds the recipient's mail server, using DNS again, by the way, and it pushes the email over to it. The recipient server accepts the mail and drops it into their inbox where it just waits to be collected. It's a whole server-to-server relay race. And this difference is so key, it all comes down to push versus pull. SMTP is the postal worker who delivers the mail to the post office. It's a push system. But protocols like POP and IMAP, well, that's what you use to go to the post office and pick up your mail. They pull the messages from the server down to your device so you can actually read them. Two completely different jobs, two different types of protocols. So let's just step back. In just a couple of clicks, we've interacted with at least 3 completely different, highly specialized systems. It's not one single internet, is it? It's really an invisible symphony of protocols, all working in perfect harmony to create this seamless experience for us. So let's just recap that journey real quick. It all started with translation, right? DNS acted as our phone book to find the correct address. Then came the conversation, with HTTP handling that polite back and forth to request and deliver the web page. And when our task changed to sending an email, a whole new system, SMTP, took over to push that message all the way to its destination. And that is really the key takeaway here. What feels like a single, instantaneous action to you and me is actually built on all these layers of complex, hidden conversations happening between machines all over the world. It's a testament to some incredible engineering that it all works so flawlessly, so quickly, that we never even notice it's happening. So the next time you click a link, just take a second to appreciate that incredible, invisible journey that's taking place. It really makes you wonder, doesn't it? What other hidden systems and silent conversations are happening all around us, powering the technology we rely on every single day? Something to think about.
You ever just stop and think about what actually happens when you click a link?
Yeah.
Or, hit send on an email. It feels instantaneous, right? Like pure magic. But underneath all that smoothness, there's this incredibly complex, hidden conversation happening. It's all based on these fundamental languages your computer is speaking constantly. So today we're doing a deep dive into those languages. Specifically, we're unpacking HTTP, that's Hypertext Transfer Protocol, and SMTP, the Simple Mail Transfer Protocol, and also DNS, the Domain Name System. These are basically the unsung heroes that make your whole internet experience possible. Our mission here is to sift through our research, pull out the really key bits of info, and, well, reveal the clever ways these protocols solve problems. We'll look at how they all work together so seamlessly to give you the digital world you use every day. Get ready for some real aha moments, I think. Okay, so let's dive right in. Let's start with the absolute bedrock of the modern web, HTTP. You could maybe think of HTTP as the internet's main communication method for websites.
That's a good way to put it. When you want a web page, your browser, that's the client, it sends out an HTTP request. And then a web server somewhere, maybe running Apache or Microsoft ISIS, it serves back an HTTP response, quick as it can.
Right.
And a really key thing to grasp is that HTTP doesn't do this in a vacuum. It relies on TCP underneath.
TCP, Transmission Control Protocol, the reliable one.
Exactly. The one that makes sure data actually gets there, point A to point B, reliably. So before any HTTP stuff happens, your browser, the client, has to set up a TCP connection with the server first.
Okay.
That connection uses something called a socket. You can picture it like a dedicated digital doorway
Okay.
through which all those requests and responses flow. And because TCP handles the reliability part, making sure data arrives complete, in the right order, HTTP can just focus on the actual content, the what.
Got it. Now, one thing you often hear about HTTP is that it's stateless. What does that actually mean?
Yeah.
And, why is that important?
Right, stateless. It sounds technical, but the core idea is simple. HTTP doesn't keep any memory, any information about clients between interactions. So every single request your browser sends is treated by the server as if it's the very first time it's ever heard from that browser. This simplicity actually makes the protocol really efficient, especially for handling huge numbers of users. It scales well, but yeah, it creates an obvious problem too.
Yeah, it does, because my immediate thought is, well, if every request is totally new, how on earth do websites remember me? Or like what I put in my shopping cart 5 minutes ago.
Exactly. That's the puzzle. And the solution that emerged is cookies.
Cookies. Right, not the tasty kind.
No, not those. These are the ingenious fix for user identification, for personalization.
Yep.
Basically, the first time you visit a site, the server can include a small piece of data, the cookie, in its HTTP response.
Okay.
Your browser then just squirrels that away in a special cookie file on your computer. Then, on every future request you make to that same website, your browser automatically includes that cookie in the HTTP request header. That lets the website's back-end database go, yes, user number 12345, and tailor the experience, remember your cart, keep you logged in, all that stuff.
So the state isn't held by the protocol, it's held by the server using this cookie identifier.
Precisely. And just quickly, for really short-term stuff, like within a single browsing session, sometimes things called session variables are used too, but cookies are the main mechanism for remembering you across visits.
Okay, that makes sense. So that stateless nature is about the protocol itself. What about the connection, the TCP connection underneath? Does that just stay open all the time, or?
Good question. That actually depends on the type of HTTP connection being used. There are two main types. First, you had non-persistent connections. These were common back in the HTTP 1.0 days.
Okay.
With non-persistent, each TCP connection is opened, used for one single request and its response, and then immediately closed.
Wow.
So imagine a web page with, say, the main HTML file and maybe 10 images. That would mean opening and closing 11 separate TCP connections.
That sounds really inefficient, all that opening and closing.
It was. Each connection requires that TCP three-way handshake to get started, which adds delay. So for every single little object, you add this round-trip time delay. It really adds up.
Yeah.
Now, browsers tried to work around this a bit by opening several connections simultaneously to download different parts of the page at once, but still, lots of overhead.
So what was the improvement?
Persistent connections. This became the default, more or less, with HTTP 1.1.
Right.
Here, the idea is simple. After the server sends a response, the TCP connection is left open. This allows more requests and responses to travel over that same already established connection. So an entire web page, the HTML, all the images, the scripts, can often be downloaded using just one single TCP connection.
Much better.
Way better. And you can even send multiple requests back-to-back without waiting for the previous response to finish, a feature called pipelining, though that had its own complexities. The server usually just closes the persistent connection after a certain period of inactivity, like a timeout. This was a huge boost for web speed.
Okay, so speaking of those requests and responses traveling back and forth,
Yeah.
they're not just random streams of data, right? They have a defined structure.
Oh, absolutely. Very defined. An HTTP request message has a clear format. It starts with a request line.
Request line.
Yeah, this tells the server the method, the action you want it to take. Most common are GEAT for just retrieving data, and POST for sending data to the server, like filling out a form. That line also includes the path to the specific resource you want, like images logo.png and the HTTP version being used.
Okay.
Following the request line or header lines, these provide extra context. Things like what browser you're using, maybe your preferred language, the host you're trying to reach, information about cookies.
Got it. And the response from the server. Similar structure.
Similar, yes, but with different components. An HTTP response starts with a status line.
Status line. Like the famous 404.
Exactly. The status line includes the HTTP version, then a numeric status code, and a short text reason phrase. So 200 OK means success. 44 not found means the resource isn't there. You might also see 301 moved permanently, which tells the browser the page has a new address, usually provided in the location header that follows. Or 400 bad request if something was wrong with the request itself. Or 505 HTTP version not supported.
Okay.
After the status line, you get response header lines. These give details like the date and time of the response, what server software is running, when the requested file was last modified, the type of content being sent like text TML or image peg and its size. And then finally, if the request was successful and there's content to send back, you get the entity body. That's the actual HTML page or the image file or whatever was requested.
Right. Okay. So you've got all these requests flying around, responses coming back. How does the internet cope with popular stuff? Like, how does it speed up delivery and stop the whole thing grinding to a halt when everyone wants the same cat video?
Haha, right. That's where web caching comes in. It's absolutely crucial.
Caching, so storing copies closer to the user.
Exactly. A web cache, which is often called a proxy server, is basically a server that sits somewhere between you, the client, and the original web server, often called the origin server.
Okay.
It intercepts your HTTP requests. If it has a recent copy of what you're asking for already stored locally,
It just sends you that copy.
precisely. It responds directly on behalf of the origin server. This is obviously much faster because the data doesn't have to travel all the way back to the origin and then back to you. It also massively reduces traffic on the core internet links.
I see.
If the cache doesn't have a copy or its copy is too old, then it will forward the request to the origin server, get the response, send a copy to you, and store a copy itself for the next time someone asks.
And those content distribution networks, CDNs, they're basically just massive networks of these caches, right?
That's exactly what they are. CDNs strategically place cache servers all over the globe, often very close to end users within ISP networks, to make content delivery super fast and reliable.
Okay, but you mentioned if the copy is too old. How does the cache know if the original file back on the server has changed? You don't want to serve stale, outdated information.
That's the key challenge with caching. Freshness. And there's a very clever mechanism for this called a conditional GET.
Conditional GET.
Yeah. When your browser or a cache wants to check if its stored copy is still valid, it sends a regular GET request, but it adds a special header line, if modified since.date.
So it's asking.
It's essentially asking the origin server, hey, has this file been changed since this date I last downloaded it?
Okay.
If the origin server looks at the file and sees it hasn't been modified since that date, it doesn't send the whole file back again. Instead, it sends back a very small, very efficient response. 304, not modified.
304. And it's empty.
Right, the response body is empty. It just tells the cache, yep, your copy's still good. Go ahead and use it. This saves a huge amount of bandwidth because you avoid retransmitting the entire file unnecessarily.
That's really smart. Okay, so HTTP 1.1 with persistent connections and caching, that sounds pretty good. But the web keeps getting more demanding, right? How did HTTP evolve further?
It did. Even with persistent connections, HTTP 1.1 could suffer from something called head-of-line blocking.
Head-of-line blocking.
Yeah. Imagine you request several things over that single persistent TCP connection, say, a big image and some small text files. If the server starts sending the big image first, and that takes a while, the smaller files get stuck waiting behind it, even though they might be ready to go. The whole line is blocked by the thing at the head.
Okay, I can see how that would make pages feel slow sometimes.
Exactly. Now, the workaround in HTTP 1.1 was often for browsers to just open multiple parallel TCP connections to the same server, maybe 6 or 8 connections.
Trying to bypass the blocking by having more lines?
Sort of, yeah. But having tons of parallel TCP connections can actually mess with TCP's own congestion control mechanisms. It can sometimes make network congestion worse overall. It wasn't an ideal solution.
So, almost like trying to fix a traffic jam by just adding more lanes, which doesn't always work and can cause other bottlenecks.
That's a great analogy, yes. And that inefficiency, that sort of conflict with TCP's goals, was a big motivator for HTTP2.
Okay, so what did HTTP2 do differently?
HTTP2 took a radical approach. It said, no, we're going back to using just one single TCP connection per server.
One connection? But wouldn't that bring back the head-of-line blocking problem?
You'd think so, but here's the genius part. HTTP2 introduces a new layer. It breaks down every single HTTP request and response message into much smaller independent pieces called frames.
Frames up.
And then it interleaves these frames from different requests and responses onto that single TCP connection.
Interleaves, like shuffling cards together.
Exactly like shuffling cards. So frames from that big image download can be mixed in with frames from a quick text download or frames from your chat messages. They all flow concurrently over the one connection. If one resource is slow to generate or transfer, its frames don't block the frames from other resources. It effectively eliminates head-of-line blocking at the HTTP level.
Wow. Okay, that sounds like a massive improvement for responsiveness.
It was huge. Plus, HTTP2 added other cool features, like letting the client prioritize certain requests, defining dependencies between resources, and even allowing the server to proactively push resources to the client it thinks it will need without waiting for a request.
Server push.
Yeah.
Interesting. So anticipating what I'll need next.
Yeah, potentially saving another round trip time.
Okay, that's a big leap with HTTP2. So what's the next chapter? What's HTTP3 about?
Right, HTTP3. This was standardized quite recently, June 2022. And this is arguably the biggest change yet because HTTP3 throws out TCP entirely as its underlying transport.
Throws out TCP? Wow. What does it use instead?
It uses a new transport layer protocol called QUIC.
QUIC. QUIC. Why build on something totally new instead of, just making TCP even better?
Well, QUIC tries to solve some fundamental limitations of TCP, especially for the modern web. It's built on top of UDP, the User Datagram Protocol.
UDP, isn't that the unreliable one?
Traditionally, yes. UDP itself is very basic, very fast, but doesn't guarantee delivery or order. But QUIC builds reliability on top of UDP. It implements its own sophisticated congestion control, error recovery, making it reliable like TCP.
Okay, so reliable like TCP but built on UDP. What's the advantage?
Several big ones. First, faster connection setup. Establishing a secure TCP connection often takes multiple round trips. QUIC can often do it in just one, especially if you've connected before. That cuts down latency right from the start.
Zero speed.
Speed, yes. Second, it tackles head-of-line blocking at the transport layer, not just the application layer like HTTP2 did. Remember how TCP ensures order? If one TCP segment gets lost, everything behind it has to wait, even if those later segments belong to a completely different HTTP stream, like in HTTP2. QUIC doesn't have that problem because its streams are independent at the transport level. If a packet for one stream gets lost, it only blocks that stream, not others running over the same QUIC connection.
Okay, that's subtle but sounds important.
It is. Plus, QUIC connections are encrypted by default using TLS 1.3, enhancing security. And it handles those multiplex streams like HTTP2, but more robustly. It's really designed from the ground up for the secure, high-performance, multiplexed world of modern web traffic.
So QUIC is like a supercharged, secure, more resilient pipeline specifically for web stuff.
That's a great way to think about it. And HTTP3 is simply the standard for running HTTP semantics over this new QUIC transport.
Fascinating. Okay, so that's HTTP handling the web. What about something equally fundamental like email? How does that magic happen? Getting a message from my outbox to someone else's inbox, maybe halfway across the world, often in seconds, even if they're not online right then.
Right, email. It feels simple to use, but yeah, the underlying system is pretty robust. It relies on basically three main components. You've got your user agent, that's your email program, like Outlook or Gmail's web interface. Then you have mail servers. These are the powerful workhorses behind the scenes. And finally, the protocol that connects them for sending mail. SMTP, the simple mail transfer protocol.
Okay, user agent, mail servers, SMTP. What are the mail servers actually doing?
The mail servers are the core infrastructure. They're like the digital post offices and sorting centers.
Right.
They have several jobs. They provide mailboxes for users to store received messages. They handle the crucial task of exchanging emails between different mail servers across the internet. And they offer what's called a best effort delivery service.
Best effort. What does that mean?
It means if you send an email, your mail server will try to deliver it to the recipient's mail server. If that server is down or busy, yours won't just give up immediately. It'll queue the message and keep retrying to connect and deliver it, maybe for hours or even days.
Persistent.
Exactly. It tries its best. Eventually, if it consistently fails after a long period, it might give up and send you a bounce message, but it really tries first. And when a server receives mail destined for one of its users, it places it into that user-specific mailbox.
Okay, so the servers are the backbone. What about the user agent part? That's just my software, right?
Yep. The user agent is simply the software you interact with directly, your Gmail tab, your Outlook application, Apple Mail, whatever. It lets you read messages, compose new ones, reply, forward, organize them into folders, save drafts, all the things you typically do with email. Crucially, it communicates with the mail servers, sending your outgoing mail to your server and retrieving incoming mail from your server's mailbox.
And SMTP is the glue for sending.
SMTP is the protocol specifically for transferring email messages between servers and also from your user agent to your outgoing mail server. It's an application layer protocol, just like HTTP. And like HTTP, it typically uses TCP underneath to ensure that reliable end-to-end delivery. Interestingly, a mail server often runs both the client side and the server side of SMTP.
Both. How does that work?
Well, it needs the server side to receive incoming mail from other servers, and it needs the client side to send outgoing mail to other servers.
Yeah, okay, so walk me through it. I hit send on an email. What's the step-by-step using SMTP?
Okay, so you compose your message in your user agent and hit send. Your user agent sends the message to your designated outgoing mail server using SMTP.
Got it. Step one.
Your outgoing mail server receives it and puts it in an outgoing message queue. Then the client side of your mail server looks at the recipient's address, like someone at example.com, it uses DNS, we'll get to that, to find the IP address of the mail server responsible for example.com.
Okay, finds the destination server.
Yep. Then your server's SMTP client initiates a TCP connection directly to the SMTP server side of the recipient's mail server.
Direct connection, server to server.
Direct TCP connection. Once that's established, your server sends the email message across using SMTP commands, things like mail from RCPTTO data. The receiving server accepts the message, and assuming everything checks out, recipient exists, etc., it places that message into the recipient's mailbox on that server.
And then the recipient eventually sees it when they check their email.
Exactly. When the recipient opens their user agent, it connects to their mail server using different protocols, usually IMAP or POP3, and retrieves the message from their mailbox.
You mentioned something interesting there, the resilience, if the recipient server is down.
Right. This is a key point about SMTP. The transfer is really designed to be end-to-end between the sending and receiving mail servers. If your server tries to connect to the recipient server and it's offline or refuses the connection, your server doesn't just hand the message off to some intermediary server in the middle.
No middleman.
No. It holds onto that message in its queue and periodically retries connecting directly to the final destination server. For quite a while, usually. That makes the delivery path very direct and accountable.
So it's not like the regular postal service where a letter goes through multiple sorting offices. It's more like a dedicated courier who keeps knocking on final door until someone answers.
That's a perfect analogy, yes. And the message format itself in SMTP is pretty straightforward. It consists of header lines first, like to, from, subject, followed by a mandatory blank line, and then the actual message body, the text you wrote.
Okay. Now, you made a distinction earlier. SMTP is for sending to servers and between servers. How does my email client get the mail? You said that's different.
That's a crucial difference, yes. SMTP is fundamentally a push protocol.
Push.
Meaning the sending server actively pushes the message over to the receiving server. It initiates the transfer and sends the data.
Okay.
But when you want to read your email, your user agent needs to retrieve messages that are sitting in your mailbox on your incoming mail server. That requires a pull mechanism.
Ah, pull, like fetching.
Exactly. So your email client uses different protocols for that, typically IM, Internet Message Access Protocol, or the older POP3, Post Office Protocol. These allow your client to connect to the server and pull the messages down to your device. Or if you're using webmail like Gmail in your browser, it's often using protocols like HTTP or specialized APIs to fetch and display your mail.
Push for sending, pull for receiving. Got it.
Two distinct operations in the email lifecycle.
Okay, we've covered how HTTP gets web pages and how SMTP sends emails between servers, but there's a huge piece missing. When I type google.com into my browser, or when my mail server needs to send to example.com, how does anything actually know where that is on the internet? We use these nice, easy names, but computers need numbers, right? IP addresses.
Precisely. You've hit on the exact problem. Host names like www.google.com are great for us humans, memorable, relatively easy to type. But for the routers and machines that actually shuttle data across the internet, those names are meaningless.
They need the address.
They need the IP address. That numerical label like 172.217.160.142 or an IPv6 address tells them exactly which machine on the network they need to route the data packets to. But we can't remember those numbers.
No way.
So how do we bridge that gap between human-friendly names and machine-required addresses? That's precisely the job of the domain name system, or DNS.
DNS, the Internet's phone book.
That's the classic analogy, and it's pretty accurate. DNS acts as this massive distributed directory service for the Internet. Its absolute core function is to translate the host names we type, like www.example.com, into the corresponding IP addresses, like 192.0.2.1, that computers actually need to establish connections.
Okay, so how does my computer use DNS? Is there like a DNS app running?
Sort of. Every internet-connected device, your laptop, your phone, even your smart fridge, maybe runs the client side of the DNS protocol. It's usually built into the operating system.
Okay.
So when you type a URL into your browser, the browser first extracts the hostname part, www.example.com. It then hands that hostname off to the operating system's DNS client resolver.
Resolver.
Yeah, the resolver. That client code then sends a DNS query containing that hostname out onto the network, addressed to a designated DNS server.
And that server just looks it up and sends back the number.
Essentially, yes. The DNS server receives the query, looks up the host name in its database, finds the corresponding IP address, and sends that IP address back in a DNS reply to your computer's resolver.
Okay.
The resolver then passes that IP address back to the application that asked for it, your browser. Now, the browser has the numerical address it needs, and it can initiate that TCP connection, using HTTP, for example, directly to the server located at that IP address.
So there's a little delay there while that lookup happens.
There is an inherent delay, yes. The DNS lookup has to complete before the actual connection can start, but this delay is usually very small, often just milliseconds, because the system uses a lot of caching, and you typically query a DNS server that's relatively close to you on the network, like one provided by your ISP.
Okay, so translating names to IP addresses is the main job. Does DNS do anything else? Seems like such a critical system might have other roles.
It absolutely does. Beyond that core translation, DNS provides several other important services. One is host aliasing.
Aliasing, like a nickname.
Exactly. Sometimes a physical server might have a less memorable sort of internal or canonical host name like server-clustereast-1.example-hosting.com, but the website owner wants people to access it using a nice simple alias like www.example.com. DNS allows you to create an alias record, specifically a CNAME record, that points the easy name to the more complex canonical name. Your browser still gets the final IP address, but the aliasing makes things cleaner.
Okay, that makes sense.
Similarly, you have mail server aliasing. An organization might want its email address to be user@example.com, but the actual mail server might have a different name, like mail.example.com or something more complex. DNS handles this too, typically using MX records, to direct mail to the correct server, even if the domain name used in the email address is an alias. In fact, the web server and mail server for example.com could even share the same alias host name, but DNS directs HTTP traffic to one IP and SMTP traffic to another.
Right. And you mentioned big sites like Google earlier. They have tons of servers. How does DNS help with that?
Yes, load distribution. This is a really powerful use of DNS. When a very popular service, like a major search engine or a big e-commerce site, is hosted on many identical servers spread across different locations for capacity and redundancy, DNS can play a key role in spreading the traffic among them.
How does it do that?
When you query DNS for the IP address of, say, www.bigsite.com, the authoritative DNS server for bigsite.com might actually have a whole list of IP addresses corresponding to all those different replicated servers.
Okay.
Instead of just returning one IP, it returns the entire list. But here's the clever part. It often rotates the order of the addresses in that list each time it answers a query.
Rotates the order.
Yeah. So the first time you ask, server A's IP might be first. The next time someone asks, server B's IP might be first, then server C's, and so on. Most clients will just try to connect to the first IP address in the list they receive.
So by shuffling the list, DNS naturally spreads the incoming connections across all the available servers.
Exactly. It's a simple but very effective way to distribute the load without needing complex, centralized load balancing hardware for every single request. And this technique is used for distributing load across web servers, mail servers, and other pooled resources.
That's really clever. And just technically, what protocol does DNS itself use?
DNS queries typically use UDP, the User Datagram Protocol, on port 53. UDP is used because it's faster than TCP, less overhead for simple request-response transactions. Though, for larger responses or certain other operations, DNS can sometimes use TCP as well.
Okay, UDP port 53. Got it. Now, you called DNS a distributed hierarchical database. That sounds important. Why not just have one massive DNS server for the whole internet?
Oh, that would be a nightmare. Imagine if there was only one central DNS database for the entire world.
Yeah, what would be the problems?
Well, first, a single point of failure. If that one server went down, the entire internet would effectively stop working. Nobody could translate names to addresses. Catastrophic. Bad.
Second, traffic volume. That one server would have to handle billions of queries per second from every device online. Just impossible to scale.
Okay.
Third, distance and latency. If the server was in, say, California, someone in Australia would have a huge delay just querying it for any website.
Yeah.
And finally, maintenance. Imagine trying to update that single massive database with every new website or server change globally. unmanageable.
Okay, so distributed is the only way to go.
Absolutely. The distributed hierarchical design solves all those problems. It spreads the load, eliminates single points of failure, allows for local caches and servers close to users to reduce latency, and makes maintenance far easier because changes only need to be made at the relevant part of the hierarchy. It's incredibly resilient and scalable.
So what does this hierarchy actually look like? What are the levels?
There are essentially three main classes of DNS servers in this hierarchy. At the very, very top are the root DNS servers.
The root. There aren't actually that many unique root servers logically. There are only 13, identified by letters A through M. But there are hundreds, actually over 1,000 now, physical servers distributed all around the world that act as copies or instances of these 13 logical roots. They're managed by 12 different independent organizations with coordination from ICANN via INA.
And what's their job? Do they know all the IP addresses?
No, they don't know the IP address for www.google.com. Their job is much simpler. They know where to find the next level down in the hierarchy. They know the IP addresses of the servers responsible for the top-level domains.
Top-level domains,
Yeah.
like .com, .org, .net.
Exactly. So below the root servers are the top-level domain, TLD servers. There's a set of TLD servers, often a cluster for redundancy, responsible for each top-level domain, one set for .com, another for .org, another for country codes like .uk or .de, and so on.
And their job?
Their job is to know where to find the next level down for a specific domain within that TLD. So the .com TLD servers know the IP addresses of the DNS servers that are authoritative for Google.com, Example.com, Microsoft.com, and so on.
Okay, so root points to TLD.
And TLD points to the next level, the authoritative DNS servers.
Authoritative. These are the ones that actually have the answer.
Yes. These servers hold the actual DNS records, the IP addresses, mail server info, etc., for the specific domain they are authoritative for. So the authoritative DNS servers for Google.com hold the A records that map www.google.com to its IP addresses. These authoritative servers are typically managed by the organization that owns the domain, like Google managing its own, or by their hosting provider or a specialized DNS service provider, and they always maintain secondary servers for redundancy.
Okay, root, TLD, authoritative. Is that it? Where does my ISP's DNS server fit in?
Ah, good point. There's one more important player, the local DNS server, often called a recursive resolver. This isn't part of the strict hierarchy, but it's what your computer usually talks to first.
My ISP provides one.
Yes. Every ISP, university, or large organization typically provides one or more local DNS servers for its users. When your computer needs to look up a name, it sends the query to this local server first. The local server then does the hard work of navigating the hierarchy, talking to root, TLD, authoritative servers, on your behalf to get the answer, and then it caches the result for a while.
So it acts like a proxy doing the legwork for me.
Exactly. It makes the process much more efficient for end users.
Okay, let's put it together. Say I type www.example.com into my browser. Walk me through that query flow again, hitting all the server types.
Sure. It typically goes like this. 1, your computer asks its configured local DNS server, what's the IP for www.example.com?
Okay.
2, your local DNS server likely doesn't know initially, so it asks a root server, hey, where can I find info about .com domains?
Right, root points down.
3, the root server replies, I don't know www.example.com, but the servers responsible for .com are at these IP addresses list of TLD server IPs.
Okay, got the TLD addresses.
4, your local DNS server then picks one of those TLD servers for .com and asks it, okay, where can I find info about example.com?
Asking the .com manager.
The .com TLD server replies, I don't know www.example.com specifically, but the authoritative DNS servers for the example.com domain are at these IP addresses list of authoritative server IPs. Sometimes the TLD might point to an intermediate DNS server, which then provides the authoritative address, but the principle's the same.
Nearly there.
6, finally, your local DNS server picks one of those authoritative servers for example.com and asks it, okay, now what is the IP address for www.example.com?
And that one knows.
7, the authoritative server checks its records and replies with the actual IP address or addresses for www.example.com.
Yeah.
8, your local DNS server gets this final answer, passes it back to your computer, and importantly, caches it so if you ask again soon, it can answer immediately without repeating the whole dance.
That makes sense. It seems like a lot of steps, but caching must make it fast most of the time.
Caching is absolutely key to DNS performance. Results are cached at multiple levels, especially by the local DNS servers.
You mentioned recursive resolver. For the local server, are there different types of queries?
Yes, there are two main types of queries involved in that process. A recursive query is essentially telling a server, please find this answer for me, do whatever it takes, talk to whoever you need to, but bring me back the final answer. Your computer makes a recursive query to your local DNS server. The local DNS server, in turn, effectively makes recursive requests on your behalf as it traverses the hierarchy.
Okay, go get it for me.
Right. An iterative query, on the other hand, is more like, tell me the next step to find this answer. The server receiving an iterative query doesn't promise to find the final answer itself. It just provides the best pointer it has to the next server down the chain.
Try asking them.
Exactly. The interactions between the local server and the root, TLD, and authoritative servers are typically iterative. The local server asks the root, gets referred to the TLD, asks the TLD, gets referred to the authoritative, asks the authoritative, gets the answer. It iterates through the hierarchy based on the referrals it gets.
Recursive from me to my local, iterative between the servers in the hierarchy.
Got it. That's the typical pattern.
So how is all this information, the names, the IP addresses, the server names, actually stored in this DNS database? What does an entry look like?
The data in the DNS database is stored in the form of resource records, usually just called RRs. These are the fundamental data elements. Every DNS query response contains one or more RRs.
Okay, resource records.
Each RR is basically a four-part tuple. Name, value, type, TTL.
Name, value, type, TTL. What do they mean?
Okay, TTL is the time to live. It's a number, usually in seconds, that tells any server caching this record how long it's safe to keep it before it should probably discard it and ask for a fresh copy.
No.
It controls cache duration.
Right, prevents stale data.
Exactly. The name and value fields depend on the type of the record. The type tells you what kind of information the record holds.
Okay, like what types?
Well, the most common ones are type A. This is an address record. Here, name is a host name, like www.example.com, and value is its corresponding IPv4 address, like 192.0.2.1. There's AAA for IPv6 addresses.
Hostname to IP. Simple enough.
Type NS. This is a name server record. Name is a domain, like example.com, and value is the host name of an authoritative DNS server for that domain, like ns1.example.com. This is how the hierarchy directs queries.
Domain to its name server, got it.
Type CNAME. This is for canonical name records, used for that host aliasing we talked about. Name is an alias host name, like www.example.com, and value is the real or canonical host name, like webserver.example.com.
Alias to real name, huh?
Type MX. This is a mail exchanger record, crucial for email. Name is a domain, like example.com, and value is the canonical name of a mail server responsible for accepting email for that domain, like mail.example.com. MX records also have a priority value, so you can specify backup mail servers.
Domain to its mail server name. Okay. Those seem like the key ones.
They're the most common ones you'll encounter, yeah. And DNS query and response messages themselves have a specific structure, too, with sections for headers containing flags about the query response, the question being asked, the answers, the RRs found, authority records pointing to authoritative servers, and sometimes additional helpful records.
And there are tools to play with this.
Yeah, if you're curious, you can use command line tools like nslookup or dig on most operating systems to manually send DNS queries and inspect the responses in RRs yourself. It's quite insightful.
Cool. One last thing on DNS. How does a new domain, like myawesomepodcast.com, actually get into this global system in the first place?
Registration. Yeah, you can't just invent a domain name and expect it to work. You need to formally register it.
With who?
You register it through a domain name registrar. These are companies accredited by ICANN, the Internet Corporation for Assigned Names and Numbers, which oversees the overall coordination of the domain name system. There are many registrars you can choose from.
Okay, so I pay a registrar. What information do I need to give them to make my domain live?
When you register a domain, you typically need to provide them with the names and IP addresses of at least 2 authoritative DNS servers for your domain, a primary and a secondary for redundancy. These are the servers that will hold the actual RRs for your domain.
So I need to have DNS servers ready first. Or do registrars help with that?
Many registrars offer DNS hosting services themselves, or you can use a third-party DNS provider, or even run your own if you have the infrastructure. But yes, you need to tell the registrar where the authoritative servers are. You also usually provide contact information for administrative and technical purposes. Once you provide this, the registrar arranges for the necessary NS records, pointing your domain to your authoritative servers, to be inserted into the TLD server's database, like the .com TLD servers.
So the TLD servers learn where to send queries for my domain.
Exactly. And then on your own authoritative DNS servers, you need to create the specific records for your services, like an A record pointing www.myawesomepodcast.com to your web server's IP address, and an MX record pointing myawesomepodcast.com to your mail server's name, which also needs an A record.
Got it. So registrar tells the TLD where my name servers are, and my name servers hold the actual A, MX, CNAME records for my specific hosts and services.
That's the process in a nutshell.
Yeah.
Once those records propagate through the system, which can take a little time due to caching, your domain becomes resolvable across the internet.
Wow. Okay, what a journey we've taken today. It's actually incredible how these three distinct protocols, HTTP, SMTP, and DNS, just, well, mesh together so perfectly. You click a link, DNS finds the IP, HTTP fetches the page using TCP, you send an email, SMTP pushes it between servers using TCP, relying on DNS to find the recipient's mail server. It's this constant silent dance happening behind the scenes.
It really is. They each have their specific job, but they rely on each other implicitly to create the seamless experience we mostly just take for granted now.
Yeah, and understanding even just a bit about these foundational languages really does pull back the curtain, doesn't it? It's not magic. It's just incredibly clever engineering. Shows the ingenuity that built this whole interconnected world.
Absolutely. They are the quiet giants, constantly working, powering pretty much everything we do online.
So maybe the next time you're streaming something or firing off an email or just browsing, maybe take half a second to appreciate that intricate, silent choreography making it all happen. And it makes you wonder, right? As our digital world gets even more complex, even more interconnected, what are the next big challenges going to be for these protocols? Will they just keep evolving like with HTTP3, or will we eventually need entirely new ways of communicating online? What do you think that future looks like?